Swayam Prabha. Digital India. Educated India.
Hello students, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University. And in this module we are discussing about crystal field theory. We have discussed about the crystal field theory in previous two lectures and now this is the third lecture in this module. While discussing crystal field theory, in first lecture we have discussed about postulates and the crystal field splitting in various geometries of the complexes like octahedral, tetrahedral, tetragonal and square planar. In second lecture, we have seen what is crystal field stabilization energy and how to calculate the crystal field stabilization energy in various types of complexes. In this module or in this lecture, we are discussing about magnetic properties of the complexes and Jahn-Teller distortion. And in the fourth lecture, we will come across absorption spectra of complexes and some typical questions based on the entire crystal field theory. So now let us start with the magnetic properties of the complexes. While discussing the transition elements, we have seen what are the different types of magnetic properties. We will just take a glimpse of that. We divide the magnetic properties into four important types. The first type of magnetism is called as diamagnetism. Now diamagnetism is a phenomena which is shown by the molecules or the substances which have no unpaired electron. And if there is no unpaired electron, the electric field which is generated by one electron is compensated by the equal and opposite spin of the other electron. We know that when we place any substance in a magnetic field, the electrons behave as tiny bar magnets. So now in case of diamagnetic substances, the magnetic moment, which is generally denoted by mu, is equal to 0 and the magnetic susceptibility, normally denoted by a symbol chi, is extremely low or negligible. And if we increase the temperature, now since all the electrons are paired up, just by increasing the temperature does not cause any effect on the magnetic moment, and as a result this chi value is also independent of temperature in case of diamagnetic substances. And if we place this diamagnetic substance in the external magnetic field, the magnetic lines of force try to avoid this substance as compared to vacuum. Hence, the magnetic lines of force passing through the substance are less than those number of lines which are passing through the vacuum. And such substance tries to be away from the magnetic field or it aligns itself perpendicular to the applied magnetic field. These are the diamagnetic substances and these are the properties of diamagnetic substances. Coming to the paramagnetism or paramagnetic substances, the second type of magnetic property. Now this type of magnetic property is shown by those compounds or those substances which have at least one unpaired electron. Now if there is an unpaired electron, it generates its own magnetic field and it tries to align itself in the direction of applied magnetic field. As a result, the magnetic moment is always some positive value or greater than 0. Similarly, it has got significant value of magnetic susceptibility chi, which is a positive value. Also, if we increase the temperature, then what will happen? Whatever electrons they are trying to align themselves in the direction of magnetic field, they will experience the opposite forces because of the thermal collisions with increase in temperature. as a result, the value of chi or magnetic susceptibility goes on decreasing with increase in temperature. If we place such substance in the magnetic field, the magnetic lines of force prefer to pass through such substance as compared to the vacuum, and as a result, such substance will align itself in the direction of applied magnetic field. Third type of magnetism is called as ferromagnetism. We normally call it as extreme case of paramagnetism, when large number of unpaired electrons are present and they are present in the form of domains. Now domains are the regions in the substance where all the electrons are aligned in a particular direction. So in ferromagnetic substance there are certain regions like this, and if we consider this particular region, all the electrons are aligned in one direction. If we consider this particular region, all the electrons or their magnetic moments are aligned in this particular direction. When we apply external magnetic field, then all the domain, the complete domain tries to align itself rapidly in the direction of magnetic field, and as a result this shows a very strong paramagnetism called as ferromagnetism. And while discussing transition elements, we have seen that there are 3 elements in the 3D series which have got a very strong tendency to show ferromagnetic type of behavior, that is cobalt, nickel and iron. So this is an observable type of paramagnetism. We can immediately observe this. Now if we increase the temperature of such substance where the domains are there, then the size of the domain goes on decreasing with increase in temperature very rapidly. As a result, the magnetic susceptibility, which is a large positive value at normal temperature, will go on decreasing rapidly with increase in temperature up to a particular temperature called as the Curie temperature. Up to Curie temperature, there is a rapid decrease in magnetic susceptibility value because of the reduction in the size of the domains. And once the Curie temperature has arrived, then all the domains have been broken and now the substance behave as if it is paramagnetic in nature. In such case, every electron is independent of each other, and as a result, after Curie temperature, there is a small and steady decrease in chi value similar to paramagnetic substance. So a rapid decrease in chi value up to Curie temperature and slow decrease after Curie temperature. Fourth type of magnetism is called as antiferromagnetism. Now this antiferromagnetism is exactly opposite in when comparison with or in comparison with the ferromagnetism. This opposite nature can be observed very clearly when we increase the temperature. See, in antiferromagnetic substances, the electrons are paired in adjacent atoms and the substance behave as if it is diamagnetic at low temperature. But when you go on increasing the temperature, the value of chi goes on increasing up to a temperature called as the Néel temperature Tn. And after Néel temperature, it behaves as if it is purely paramagnetic in nature, and hence the chi value goes on decreasing with temperature after the Néel temperature. This is the graph which shows behavior of 4 type of magnetic substances. The first lower graph is showing the diamagnetism or the diamagnetic susceptibility with respect to temperature, which is almost constant with increase in temperature. This third graph is showing paramagnetic behavior. This green graph is showing a ferromagnetic type of behavior, rapid decrease in magnetic susceptibility up to Curie temperature and slow decrease similar to paramagnetism after Curie temperature or above Curie temperature. And this particular graph in between is showing a Tn, which is corresponding to antiferromagnetic substance, where there is an increase in magnetic susceptibility up to a particular temperature called as the Néel temperature, and after that it behaves similar to paramagnetic type of substance. Now we have also discussed that magnetic nature or magnetic behavior of a substance is measured in terms of magnetic moment. Now we know that when we place any substance in external magnetic field, the electrons will try to align in the direction of magnetic field because electron is behaving as a tiny bar magnet. Now electron has two types of motions, the spin motion around its own axis and the orbital motion around the nucleus. So when we place this electron or this substance in the external magnetic field, it tries to align both of its motions in the direction of magnetic field. So it can adopt spin motion in the direction of applied magnetic field as well as orbital motion. We will see how the spin motion can be aligned in the direction of magnetic field. So if we have a tiny bar magnet like electron and we apply external magnetic field, now this is having a spin motion. As a result, it behaves as a tiny bar magnet with its magnetic moment aligned in a particular direction. Now when we apply external magnetic field, it starts rotating in such a way that the magnetic moment vector is parallel to the applied magnetic field. As a result, it contributes to the magnetic moment or total magnetic moment of the substance by adopting spin motion in the direction of applied magnetic field. Second way of aligning in the direction of magnetic field is by adopting orbital motion in the direction of magnetic field. Now how the orbital motion can be aligned? We know that electrons are orbiting in various orbitals. For example, an electron is present in suppose dxy orbital. Now this dxy orbital is in the xy plane and there is no z component in this orbital. And if we apply external magnetic field along z direction, then this orbital can rotate by 90 degrees into dyz orbital. Now this orbital has a z component because now it is in the yz plane. Thereby the electron which is present in this orbital has now z component. So it has aligned itself in the direction of magnetic field by adopting orbital motion in the direction of applied magnetic field. So this is how electron behaves when external magnetic field is applied. Now as a result, the total magnetic moment is a sum of spin as well as orbital magnetic moment, and the magnetic moment or the resultant magnetic moment or total magnetic moment is given by this particular formula. This we have already discussed while discussing the transition elements or 3D series elements. Whereas in case of lanthanides and actinides, we have seen that the things are a bit complex and there is a spin orbit coupling leading to the effective magnetic moment given by mu j, which is equal to g into under root of j into j plus 1. That is, j is called as the total orbital angular magnetic moment or total orbital angular momentum quantum number, and small g is called as the Landau splitting factor. Now in case of 3D series element, the orbital motion is completely quenched because of very strong interaction with the ligands. As a result, this L part is not considered and the spin only magnetic moment is given by formula under root of 4 s into s plus 1, and we know that for n number of electrons this total spin quantum number will be n by 2, and as a result we can calculate mu s is equal to under root of n into n plus 2 Bohr magneton. This we have already discussed in case of transition elements or the magnetic properties of transition elements. Now we move forward to the complexes. Consider the octahedral complexes with configuration D1, D2 and D3. Now in this case, if you have octahedral complexes, we know that the splitting of d orbitals has T2g and Eg, and if there is only one electron, it will be definitely present in T2g, and in case of T2g there are 3 orbitals, hence this electron remains unpaired, and since it remains unpaired, the spin only magnetic moment is given by under root of n into n plus 2, which comes out to be 1.73 Bohr magneton. Hence the substance is paramagnetic in nature in case of D1 system. Similarly, in case of D2 system, the 2 electrons are present in T2g orbital. Since there are 3 T2g orbitals, both the electrons remain unpaired and magnetic moment or the spin only magnetic moment, which is calculated as 2.83 Bohr magneton. Similarly, in case of D3 system, you have all the 3 electrons in T2G and all the 3 are unpaired. As a result, the magnetic moment or spin only magnetic moment comes out to be 3.88 Bohr magneton. So all the 3 are paramagnetic in nature, and these are the examples of the metal ions which are involved in D1, D2 and D3 configurations. Coming to D4, D5, D6 and D7 configurations. Now we have already discussed that in case of D4 to D7 configuration, there are two possibilities. If the ligand is weak, then the complex is said to be high spin complex. And in case of high spin complex, all the electrons remain unpaired as present in the free metal ion. So in case of D4 configuration, the high spin configuration is T2G3 Eg1 and all the 4 electrons are unpaired. As a result, the magnetic moment is 4.9. Whereas in case of D5 high spin, all the 5 electrons are unpaired and magnetic moment will be 5.92 Bohr magneton. In case of D6 configuration, the configuration is T2G4 Eg2. Now out of this, there are only 3 T2G orbitals and there are 4 electrons. It means that there is 1 electron paired. As a result, there are only 4 unpaired electrons and the magnetic moment has reduced to 4.90. In case of D7 system, T2G5 Eg2, now 5 electrons are there. It means that 2 pairings have already taken place. So only 1 unpaired electron over here and 2 unpaired electrons in Eg. So total 3 unpaired electrons, leading to magnetic moment of 3.88 Bohr magneton. In case of low spin complex, D4 system, since the electrons are paired up in the lower orbital, there are only 2 unpaired electrons. As a result, the magnetic moment is 2.83 Bohr magneton. In case of T2G5 configuration, that is D5 configuration, all the 5 electrons are in T2G in case of low spin state, and there is only 1 unpaired electron present over here. As a result, the magnetic moment will be 1.73 Bohr magneton. While in case of D6 system, the configuration is T2G6. All the 6 electrons have been paired up and there is no unpaired electron, hence magnetic moment is 0. The substance behaves as a diamagnetic substance. And in case of D7 system, there is 1 unpaired electron in Eg. As a result, the magnetic moment is 1.73 Bohr magneton, and again it is paramagnetic. So most of them are paramagnetic except D6 low spin state. Coming to D8, D9 and D10, again you have, in case of D8 system, the 6 electrons are already paired up in all the 3 systems, whereas in this case there are 2 unpaired electrons, in this case there is 1 unpaired electron, whereas in this case there is no unpaired electron. As a result, the magnetic moment goes on decreasing from 2.83 to 1.73 to 0 when we go from D8 to D10 system. And in this case, there is only one possible configuration. There is no high spin or low spin state. And in this case, you can see that this D10 system is diamagnetic in nature, and so all the complexes of Zn2 positive will be diamagnetic in nature. Now coming to the magnetic properties of tetrahedral complexes. Now we know that for tetrahedral complexes, the value of delta T, that is the crystal field splitting energy, is of the order of only 0.45 delta O. So it's much less or less than 50% of delta O value. As a result, this is always less than the pairing energy. And we have already discussed that when the crystal field splitting energy is less than the pairing energy, then pairing is never preferred, and as a result, all the complexes of tetrahedral geometry are high spin complexes. And in high spin complexes, they contain exactly equal number of unpaired electron as that of the free metal ion, and hence the magnetic properties will be definitely corresponding to the high spin complexes. Coming to the magnetic properties of octahedral complexes for 4D and 5D series elements. Now most of the examples what we have seen are corresponding to the 3D series elements, and in case of 3D series elements, we have seen that the magnetic moment is mainly because of the spin only contribution, and there is no orbital contribution to it. But in case of 4D and 5D series, we have already discussed the factors which affect the crystal field splitting energy. In case of crystal field splitting energy of 3D to 4D to 5D, when we move, we have observed that this delta O value goes on increasing from 3D to 4D to 5D systems, and as a result, for 4D and 5D system, the delta O is always less than pairing energy, and since delta O is less than pairing energy, the complexes which are formed must be low spin complexes. Consider this case. This is an interesting example. These are the two complexes of cobalt in +3 oxidation state with two different ligands. H2O is a weak ligand, NH3 is a stronger ligand, and then you have rhodium and iridium forming complexes with the strong ligand, that is NH3. Now the mean pairing energy is of the order of 21,000 centimeter inverse. Consider the first two complexes. If you have COH2O6 3 positive, the value of delta O is 18,200 centimeter inverse, while the mean pairing energy is 21,000 centimeter inverse. It means that pairing will not be preferred and the complex will be high spin in nature. Whereas when we go to CONH363 positive, the value of delta O is larger because of stronger crystal field splitting due to stronger ligands. And as a result, this delta O value is now more than the pairing energy. As a result, the pairing is preferred and this is now a low spin complex. But when we go to rhodium and iridium, which are corresponding to 4D series and 5D series, the value of delta O is much larger as compared to the mean pairing energy. And since the value of delta O is much larger, always the complex will be low spin in nature irrespective of the ligand. Whether it is H2O or whether it is NH3, it doesn't matter because the mean pairing energy is much less as compared to delta O, and as a result pairing is always preferred and all the complexes of 4D and 5D series element with octahedral geometry are low spin complexes. Then one more aspect to this magnetic moment studies is the quenching of orbital contribution to magnetic moment. We have seen that there is, in case of 3D series elements, the magnetic moment consists of only one contribution, which is the spin only contribution, but in case of 4D and 5D there is an orbital contribution to magnetic moment. Now we will see how this magnetic moment or orbital contribution will take place. Now we know that T2G orbitals can transform into one another and hence can contribute to the magnetic moment, while EG orbitals cannot transform into each other and hence they cannot contribute to the magnetic moment. And if T2G orbitals are symmetrically filled, the rotation does not cause any change and hence the orbital contribution is zero. We will try to understand these 3 points in details, taking the example of T2G and EG orbitals. Now let us consider the shapes of various d orbitals. Now we know that T2G orbitals are dxy, dyz and dxz. This dxy orbital is in the xy plane, dyz orbital is in the yz plane and dxz orbital is in the xz plane. Now EG orbitals are dx square minus y square, where this dx square minus y square orbital is in the direction of x and y axis, again in the xy plane, and dz square orbital is in the z direction. So EG orbitals dx square minus y square and dz square, T2G orbitals dxy, dyz, dxz. Now if this dxy orbital is rotated through an angle of 90 degrees, it can transform into dyz orbital. Similarly, dyz orbital can be transformed into dxz orbital by rotation through 90 degrees. Similarly, dxz orbital can be transformed into any of these. It means that T2G orbitals can be transformed into each other just by rotation by 90 degrees. But this is not possible in case of EG set of orbitals. So if there is electron in EG set of orbital, it cannot transform into another EG orbital just by rotation because the shapes are entirely different. Hence, EG orbitals do not cause any orbital contribution to the magnetic moment. Only those orbitals which have a property of rotation to transform into another orbital can contribute to magnetic moment. It means that EG orbitals have no contribution or no orbital contribution to magnetic moment at all. So forget about this. Now coming to T2G. Now T2G orbitals also can cause orbital contribution to magnetic moment in specific cases. Let us discuss the electronic configurations of these T2G orbitals one by one. If there is one unpaired electron in T2G orbital, then this orbital, if transforms into another orbital, now if we apply external magnetic field to this along z-axis, now this electron is present in dxy orbital. The applied magnetic field is along z direction. Hence, this cannot contribute to the magnetic moment at this time or at this particular moment, because this electron has an orbital motion in the xy plane. In such case, this orbital will transform by rotation by 90 degrees into either dyz or dxz orbital which have z component in them. As a result, now the electron will be present in either dyz or dxz orbital. It means that the electron has occupied an orbital or transformed from an orbital which is dxy into another orbital which is dyz, and this orbital has a z component in it. As a result, this is called as orbital contribution to magnetic moment. Now it can contribute to the magnetic moment. So this is called as the orbital contribution. So apart from spinning in the direction of applied magnetic field, it is causing its orbital motion in the direction of magnetic field. Similarly, so it means that if you have T2G1 configuration, it will definitely cause orbital contribution. Similarly, if you have two electrons in T2G set present in dxy and dyz orbitals, then both of them or any one of them can transform into another. Thereby, initially you have one electron in the dxy orbital which was not contributing towards the z direction, but now you have both the electrons along the or in the direction of z axis because of the dyz and dxz orbitals. Hence, this can also contribute to the magnetic moment. But if the three orbitals are symmetrically filled with T2G3 configuration, so each of the three orbitals have unpaired electron now. Now just by transforming one orbital to another cannot cause any orbital contribution to magnetic moment, because this orbital is already having unpaired electron. So if there is a transformation from this to this or this to this, simultaneously there will be opposite transformation from this to this. As a result, total number of electrons which are having z component in them will remain only 2. As a result, there will be no orbital contribution to magnetic moment, or we can say that the orbital contribution is quenched in case of T2G3 set. Coming to T2G4, you have two electrons over here. So now if it transforms into another orbital, definitely there will be more number of electrons along z direction. Similarly, if you have T2G5, again you can have more number of electrons along z, because this can now transform into dxz orbital and it can have 4 electrons. Initially you have only 3 electrons in having z component. Now this can transform into this and you can have 4 electrons with z component. Hence T2G5 will also have an orbital contribution, but T2G6 cannot have orbital contribution because transformation of one orbital to another cannot lead to increase in the number of electrons having z component in them. So orbital motion is quenched in T2G3 and T2G6 complexes. In other words, we can say that if T2G orbitals are unsymmetrically filled, there will be orbital contribution, and if T2G orbitals are symmetrically filled, the orbital motion is quenched. Coming to an important concept of what is called as a Jahn-Teller effect or Jahn-Teller distortion. Our professor used to pronounce it as Jahn-Teller distortion. He used to say that this J should be pronounced as year. Okay, anyway, we will call it as a Jahn-Taylor distortion. It is based on a theorem called as Jahn-Taylor theorem. It says that any nonlinear molecular system possessing degenerate electronic state will be unstable and will undergo distortion to form a less symmetrical system and will remove the degeneracy. Consider this example of CuH2O6 positive, which is a D9 system. We'll try to understand this theorem in terms of this particular complex. Now, since it is a D9 system, it has to have T2G6 and Eg3. So there are 3 electrons in Eg orbitals. Now Eg orbitals are dx square minus y square and dz square. So now out of the 3 Eg orbitals or Eg electrons, 2 can go to dx square minus y square and 1 can go to dz square, or 2 can go to dz square and 1 can go to dx square minus y square. As a result, the ligands which are coming along x, y and z axis, because it's an octahedral complex and ligands are approaching along the axis, so these ligands will experience different force of repulsion along the xy plane and along the z axis because the number of electrons are different. As a result, there will be further splitting of these orbitals or Eg set of orbitals as well as T2G set of orbitals. Let us see what happens. This is a perfectly octahedral geometry, and if the ligands are experiencing more force of repulsion along z axis, then there will be elongation along the z axis. As a result, the perfectly octahedral geometry converts into a distorted octahedral, or what we call as a tetragonally distorted octahedral geometry, and as a result there is a further splitting of d orbitals, like Eg set of orbitals split into dz square and dx square minus y square. Now dz square decreases in energy because there is now less repulsion along z axis. Similarly, the dxz, dyz will lower in their energies because z axis is experiencing, or the z orbitals are experiencing less force of repulsion, and this leads to a distortion. Now if we calculate the total net loss or gain of energy, there are 2 electrons in dz square and 1 electron in dx square minus y square. As a result, there is a net release of energy by a factor of 1/2 delta 1, and hence this acts as a driving force for distortion, and definitely distortion will take place in order to release this much of energy. This is called as Jahn-Taylor distortion. Exactly opposite will be the case if there is a compression along z-axis. If the 2 ligands along z-axis are getting compressed, in that case the energy of dx square minus y square will decrease while the energy of dz square will increase. As a result, the 2 electrons will be there in dx square minus y square, and there will be net stabilization by again a factor of minus 1/2 delta 1. Such case will be there, and dxy orbital in the T2G set will decrease in its energy, while dxz and dyz orbitals will increase in energy. Now Jahn-Taylor distortion will take place only in specific cases. There are certain cases where there is a symmetrical distribution of electron charge. In such case, there will be no distortion at all. For example, if we consider D0 system where T2G and Eg are completely symmetrically filled, D3 system where T2G has 3 electrons and Eg has no electron, D5 high spin state where T2G is having 3 electrons and Eg is having 2 electrons, both of them are symmetrically filled, D6 low spin state where T2G is with 6 electrons and Eg is 0, again it is symmetrically filled, D8 system T2G with 6 electrons, Eg with 2 electrons, and D10 system where both T2G and Eg are completely filled. In all these cases, the electronic distribution is symmetrical, and so Jahn-Taylor distortion will not take place. Now second condition is the strong distortion condition where Eg set of orbitals is unsymmetrically filled. Now we know that Eg orbitals are directly in the path of the ligand, the dx square minus y square and dz square. They are directly facing the ligand in case of octahedral complex, and as a result, if Eg set of orbital is unsymmetrically filled, there will be strong distortion. Such configurations are D4 in the high spin state, Eg is having 1 electron, D7 In the low spin state, again Eg is having one unpaired electron, and D9, the copper complex just now we have seen with Eg3 configuration. So there will be strong distortion or large distortion. While the third case is slight distortion condition where the T2G sets are unsymmetrically filled. Now, if T2G orbitals are unsymmetrically filled, we know that T2G orbitals are not directly facing the ligand, and hence if they are unsymmetrically filled, there will be slight distortion in the geometry, like D1 system, D2 system, D4 system in the low spin state, D5 system in the low spin state, D6 system in the high spin state, and D7 system in high spin state. In all these cases, the Eg is symmetrically filled, but T2G are unsymmetrically filled, and in such case there will be slight distortion taking place called as the Jahn-Taylor distortion. So this is all about this lecture. We will continue the remaining topic in our last lecture, which is lecture 4. Thank you very much.